Have you ever looked at your brand new super powerful computer and just wondered why it still feels kind of slow sometimes? You've got all this horsepower under the hood, but you feel like you're stuck in traffic. Well, today we're going to pull back the curtain and figure out why that happens and explore the brilliant software trick that unlocks your PC's real speed.
Right? It's a feeling we all know. You get a machine with an 8-core, 12-core, heck, even a 16-core processor, and you're expecting it to just fly. But then you're still staring at that loading bar, that spinning wheel. So what gives? Is all that extra hardware just for show? Not at all. Okay, so here's the core of the issue. On the left, you've got a single-core processor. Think of it like one worker trying to do absolutely everything. Now, they might be really fast, but they can still only do one thing at a time. On the right, that's the dream of a multi-core processor, a whole team of workers, ready to jump on a job all at once. The potential is huge, but here's the problem. Most of the time, that team is just kind of sitting around waiting for something to do.
So the big question is, how do we get that team off the bench and into the game? How do we put all that incredible unused power to work? Well, the answer isn't about buying more hardware. It's all about how the software thinks.
And here's the secret. The bottleneck isn't your processor. It's that most software is, by default, written to talk to just one of those workers at a time. It gives out instructions one by one. So to really unlock your computer's power, we have to teach our software to think more like a team captain, handing out different jobs to different workers all at the same time.
And how do we actually do that? Well, we use a concept that lets a single program split itself into a whole team. They're the real heroes of our story today. It's time to meet the threads.
So what in the world is a thread? The official technical definition is a single sequential flow of control within a program. But let's be honest, that doesn't help much. A much better way to think about it is this. A thread lets a single program break itself up into lots of smaller tasks that can all run at the exact same time, each on its own little piece of the processor.
Okay, I know, that's still a little abstract. So to make this super clear, let's just forget about computers for a second and step into a really busy restaurant kitchen.
So a program with only one thread is like having just one chef. That poor chef has to do everything in a specific order. Chop the veggies, then cook the steak, then make the sauce, then plate the whole dish. It works, but it's slow. But a multi-threaded program, now that's a full kitchen staff. You've got one chef chopping, another on the grill, a third whipping up the sauce, all at once. The meal gets finished and out the door in a fraction of the time. Now that's the power of threads. But, and this is a really big but, what happens when your team of chefs isn't coordinated? What happens when two of them need the exact same ingredient at the exact same time? Well, you get total chaos. And in the world of programming, we call this a race.
This right here is the #1 problem in parallel programming. Imagine two of our chefs and they both reached for the only salt shaker on the counter. Who gets it? What if they both manage to grab it and salt the same dish without talking to each other? You end up with a disaster. In software, that salt shaker could be anything, a file, a piece of data, or say a bank account balance. Let's watch this chaotic situation, which is called a race condition, play out. We've got a bank account with $100. At the exact same microsecond, thread A tries to deposit $50 and thread B tries to withdraw $20. Okay, first step, both threads read the balance. They both see $100. Next, thread A does its math. 100 plus 50 is 150. At the same time, thread B does its math. 100 minus 20 is 80. Now, watch what happens. Thread A proudly saves its result, 150. But just a split second later, thread B saves its result, 80, completely overwriting what thread A just did. The final balance is now $80.
The final balance is just wrong. It's totally wrong. It should be $130, right? But that $50 deposit has just vanished. It's gone, completely wiped out because our threads weren't coordinated. This is the real danger here. Data getting corrupted, programs crashing, and bugs that are an absolute nightmare to track down. So, how in the world do programmers stop this digital kitchen nightmare? Well, they bring in a kind of traffic cop. It's a simple, really elegant tool that enforces one single critical rule. Only one thread gets to touch a shared thing at a time.
This little digital traffic cop is called a mutex, which is short for mutual exclusion. But honestly, you can just think of it as a lock. Before a thread can touch a shared resource, like our bank account, it has to get the lock.
And while it's holding that lock, every other thread just has to wait in line. It's a really simple rule. One at a time, please.
Okay, so let's run that bank account scenario again, but this time with a Mutex in charge. Step 1. Thread A grabs the Mutex lock for the account. Now, thread B has no choice but to wait. Step 2. Thread A can now safely read the $100 balance, add its $50, and write the new, correct balance of $150. Step 3. Its job is done, so it unlocks the Mutex. Now thread B can have its turn. Step 4. Thread B locks the Mutex, reads the correct current balance of $150, subtracts its $20, and writes the final perfectly correct balance of $130 before it unlocks. See? Order is restored. The math works.
And this combination, this elegant dance between parallel workers, our threads, and these digital traffic cops, the mutexes, this is what really unlocks the speed of the modern computer that you are using every single day.
I mean it. Threads are absolutely everywhere. When you're playing a video game, you've got separate threads for the graphics, the enemy AI, the physics, all running at once. In the web browser you're using, one thread is probably downloading images, while another one is letting you scroll the page nice and smoothly. If you've ever edited a video, you can keep working on your timeline while a totally separate thread is rendering your project in the background. This managed chaos is the invisible engine behind almost everything we do.
So if you're going to take away one thing from all this, let it be this simple idea. Threads are what give our software the power to do many things at once, unleashing the real potential of all those cores in your computer. But it's that humble little Mutex that gives us the control, the thing that stops all that incredible power from turning into just total chaos. And all of this leads to a final, really interesting thought. You know, we now have computers with 32, 64, even more cores. Our team of chefs is getting enormous. So the question for the future is, what new rules, what new ways of coordinating are we going to have to invent to manage all of that incredible complexity? That, right there, is the next great frontier in computing. Thanks for digging into this with me.